Romero from the Institute of Radio Astronomy of Argentina in La Plata. And so you have seen a lot about cosmic rays, some instrumentation, topics of physics beyond the standard model, and also extragalactic astrophysics. And Gustavo will take you through 3 lectures on galactic astrophysics at the very and ultra high energies. So thank you, Gustavo.
Okay, thank you very much, Ulises, for the presentation. As Ulises mentioned, I'm going to talk about high-energy galactic gamma-ray sources. The first 2 lectures that I am going to offer you will be focused on sources that are detected by Fermi or by HESS telescopes, and mostly sources on the galactic plane. And the last lecture will be devoted to the starlets of the moment. These are the pevatrons, recently discovered by LASSO. Several of the things that I am going to show you already were presented in these lectures, but I hope to present these things again from a different point of view in order to just fix some important concepts. Allow me to start from the very, very beginning, from what is a gamma ray. So a gamma ray is the most energetic form of electromagnetic radiation. You perhaps remember the first lecture by Felix Aharonian. He introduced some classification of the gamma rays. In low-energy gamma rays, these are gamma rays from 100 kilo electron volts up to 100 mega electron volts. I prefer to start this band not in 100 kilo electron volts, that for me are X-rays, but in 511 kilo electron volt. That number is, of course, not arbitrary. It is the rest mass of the electron. So for me, gamma rays start when a photon has the capability of producing an electron-positron pair. This is the most difficult energy band in gamma rays to observe. The last successful instrument observing in this band was COMTEL instrument on board of the Compton satellite. Compton satellite was launched in the early 90s and was deorbited in 2000. So it has been 25 years since we have a Compton telescope observing in this energy range. If we are lucky, in a couple of years, COSI will cover this energy range again. It's quite important energy range for several different physical processes. I will try to mention a few of them later. Then we have the traditional high-energy band from 100 MeV up to 100 GeV. This is the energy range covered, for instance, in the past by instruments such as COBE, the European satellite in the 70s, and EGRET, the instrument also on board of the Compton satellite in the 90s, and now by Fermi. So it is perhaps the best explored band in the gamma ray sky. Then we have the very high energy gamma rays that goes from 100 GeV up to 100 TeV, tera electron volts. And here we need to use, we cannot use any more satellites because the collecting area is not high enough as to be sensitive to the few photons of this energy range. So we need to use instruments on the Earth, atmospheric Cherenkov telescopes, such as the high-energy stereoscopic system in Namibia, or MAGIC, Veritas, and the other instruments of the kind. Then we have the ultra-high energy gamma rays that goes from 100 TeV up to 100 PeV. peta-electron volts. This is the energy range that is now being explored by LASSO. And here are the more surprising news in the last few years about gamma ray sources. I will devote to this energy range the last of my 3 lectures. And finally, we have the extremely high energy gamma rays that are above 100 PeV. These gamma rays are usually thought to come from outside of the galaxy, so I am not going to discuss these gamma rays. Okay, well, this is an image of the entire galactic plane by Fermi satellite. So it's in the energy range of high energy gamma rays. This emission is integrated above 100 MeV. And what we see here, we see a lot of diffuse emission along the galactic plane. This emission is produced by the interaction of the galactic cosmic rays. Remember the lecture by Rafael, with the gas in our galaxy. So what is this gas? Is it hydrogen, is helium, 20% more or less, and then some heavier stuff, like, for instance, CO and other molecules. So when the hadronic component of the cosmic rays interact with this gas, produce neutron pions, they decay and give us part of this radiation. This radiation was already predicted in 1953 by Hayakawa, soon after the discovery of the neutral pion. So it's a remarkable prediction in the history of high-energy astrophysics. And also Hutchinson, 1 year before, predicted that the leptonic component of the cosmic rays in the galaxy should produce gamma ray by Bremsstrahlung emission. So part of this emission also is Bremsstrahlung, leptonic emission. If we move up in energy bands, so we start to see less and less diffuse emission, and we can see more discrete sources. Actually, if you look at this image, you will see that superposed with the diffuse radiation, there are discrete sources. For instance, here you have one of the most massive stars in the galaxy, Eta Carina. And here you have Vela Jr., famous supernova remnant discovered in 1998. By the way, the radio counterpart of this remnant was discovered from my institute in Argentina. And here you have another remnant, W30, and Gamma Cygni, another one, and other sources, in particular some pulsar wind nebulae. Okay. So what are these sources? Well, the fourth Fermi-Lat catalog is the most updated version of the catalog. And in this catalog, we have thousands of gamma ray sources. Most of them are extragalactic, and they are identified with blazars. These are active galactic nuclei with powerful jets that are pointing in a direction. These are more than 60% of the sources in the catalog. Then we have some non-blazar active galaxies, galaxies that are active. They have a massive, supermassive black hole, but no jets. So, for instance, these are CLAF 1 and type 2 galaxies. Then we have also some normal galaxies, like, for instance, Andromeda galaxy, that are detected because they are very nearby, and we can detect the interaction of the cosmic rays with the local gas. And then we have the galactic sources. In this series of lectures, I will be mostly concerned with the galactic sources. So we have in the Fermi catalog supernova remnants and pulsar wind nebulae. That is more or less up to 3% of the sources. Then we have pulsars. Almost 5% of the sources are pulsars. And then we have globular cluster, gamma ray binaries, microquasars, and even some novae. Okay, what happens now if we move up in energies? If we go to the next band, to the very high energy band. So here we have the HESS Galactic Plane Survey. Well, what we are seeing here is the galactic plane as observed by the HESS system of telescopes in Namibia. This is a photograph of HESS with the large telescope at the center and the four small telescopes around. And what we see here, we see now a lot of discrete sources. Some of them are well resolved, and as you can see, we can see the morphology of these sources. This is very useful for the identification of the sources when we compare with the radiation from other wavelengths. Okay, this is the list of those sources in the HESS Galactic Plane Catalog that are already identified. We have some gamma ray binaries, systems formed by a compact object, either a neutron star or a black hole and a massive star. Then we have a number of supernova remnants that are resolved, so we know the morphology and we can match this morphology with the morphology, for instance, in radio images, and we know that effectively these supernova remnants are gamma ray sources. For instance, you have here some famous ones like Villa Junior and this one, RxJ 1713-39. Then we have the pulsar wind nebula. We have a lot of them. I would tell you more about these sources later. And we have a bunch of sources that are a combination of supernova remnants with pulsar wind nebula. So we do not know exactly how much each one of them contribute, how much to the total emission we are receiving. And then we have a lot of sources that are not identified at all. We don't know any counterpart at other wavelengths. So it's about 35 sources that are not clearly identified in this catalog. Okay, well, this is just a glimpse of the phenomenology of the field. Now, what I want to discuss is what does it take to create a high energy or a very high energy gamma ray source? The first thing that could come to your mind is, well, you can produce radiation just hitting things. For instance, if I make a fire, I produce optical photons. So perhaps I can heat a gas to the point that the temperature will be so high that it will produce gamma rays, perhaps. For instance, if a gas or the source receives as much as heat as it radiates, then it works as a black body, and then it's almost in a thermodynamical equilibrium. So we can describe the population of particles in the source as Maxwellian, as you know, and then the photon spectrum that is produced by a Maxwellian distribution will be a Planck distribution, as you know, that is characterized by a given temperature. It's the temperature of the peak in the Maxwellian, the Planckian distribution of radiation. So this is the intensity of a black body according to the Planck law. This is the energy of the photons that are being radiated. This is the temperature, and this K is the Boltzmann constant that in GHS units values approximately 1.4 times to 10 to the minus 16 erg per Kelvin to the minus 1. And H is, of course, the Planck constant. So what is the average energy of a photon of temperature T producing a gas with temperature T? T is given by this expression, is 2.7 times the Boltzmann constants to the temperature. And if we express the temperature, this energy, sorry, in mega electron volts, then we get this expression that you have here, that is the same that I have reproduced over here. So now let's think that, okay, I want to rise the temperature of this system to the point that the photons produced have, let's say, 1 giga electron volt. So if I wanted to have photons of 1 giga electron volt, this is 10 to the 3 mega electron volts, then I will need extremely high temperature. The temperature will be 10 to the 13 Kelvin. This is a huge temperature. And there is a problem with such huge temperatures. If you compute what is the photon density in your source with that temperature in a Maxwellian, in a Planckian, sorry, distribution, you will get a photon density of the order of a few times 10 to the 46, 10 to the 46 photons per cubic centimeter. This is a huge number. So the mean free pass of a photon in such an environment will be just the density of the photons times the cross-section for pair production. Why pair production? Because now we have photons of 1 GeV. And if these photons interact with other photons, we'll produce electron-positron pairs because it's well above the threshold for pair production. What is the cross-section for the photon-photon interaction? It's an electromagnetic interaction, as you know. So is the order of the Thomson cross-section, 10 to the minus 24 centimeters square. So the result will be that all photons will create pairs. They will not escape from your source. So your source will be opaque to the photons, and the result will be that a lot of pairs will be created inside the source. So this will increase the pressure of the gas, and then the system will expand. And we are creating now a fireball. What is a fireball? It's a system where photons are annihilated and are transformed into electron-positron pairs that interact, producing new photons that yield new electron-positron pairs. So the multiplicity of pairs increases as the system expands, and the temperature goes down. At some point, the system will become transparent to photons, and the photons will escape. But the energy of these photons will be below the threshold for electron-positron pair production. So they will be X-ray photons, not anymore gamma-ray photons. So the moral is that you cannot produce a gamma-ray source just heating gas. You need something that is completely out of thermal equilibrium in order to produce a gamma-ray source, an efficient gamma-ray source. Of course, you can have in the universe transient sources that are fireballs, gamma-ray bursts. You remember probably the lectures by Elisabetta on the first day on gamma-ray bursts. And also the universe at the very early epochs was also a fireball until it became transparent to photons. Okay, so if we want to produce a gamma-ray source, we need a population of particles outside the thermal equilibrium. And we need something else. We need also a target for those particles in such a way that an interaction occurs and gamma rays can be produced in this interaction. So let's have a look at the situation. Let's imagine that we have some particles that are the target. Let's call these particles B. The target has a density that is NB, And it has a volume that is the product of the length of the target times the cross-section, differential A. This is the volume of your target. And then we have some non-thermal incident particles. Let's call these particles A. And these particles impact on the target. They have a density that is Na. So the total number of interactions will be proportional to the total number of targets and the total number of particles impacting the target. And the constant, the proportional constant, is what we call the cross-section. That is the cross-section for the interaction. Since this is the interaction of kind E, whatever, bremsstrahlung, proton-proton interaction, it doesn't matter now, then we need to put here the cross-section for that specific interaction. Units of the cross-section, as you know, are centimeter square, and we usually use the barn, that is 10 to the minus 24 centimeters square, but more frequently, since cross-sections for most interactions are quite small, we use the millibarn. That is 10 to the minus 27 centimeters square. Okay, now we have the incident particles and we have our target. What we want to know now is what the gamma ray emissivity of our target. So this is the number of photons produced in the target in gamma ray regime per unit of energy, per unit of time, per unit of volume, per unit of a solid angle. And how can we calculate that? Well, the idea is that we only need to add each one of the interactions that occur. So we need to know what is the density of incident particles, these non-thermal projectiles that impact onto our target. We need to know the density of our target, and we need to know the differential cross-section. This is the cross-section as a function of energy and as a function of the solid angle. And of course, particles could come from any direction, so this is taken into account in this factor you have here. So if you know all these things, the density of your incident particles, the density of your target, and the cross-section, the differential cross-section, you can integrate this. You can add all these interactions and get the emissivity. And then when you have the emissivity, you can multiply by the square of the energy of the photons, and you can get the power of your source in gamma rays. These are just some examples of how using this simple expression and replacing each one of these things by the corresponding counterpart in the real world, we can get spectral energy distribution of real objects. For instance, here you have a source where this part is calculated by synchrotron radiation, the incidence of particles on a region with a magnetic field. And here we have the result of proton-proton interactions. These are inverse Compton upscattering of these photons, and this here is bremsstrahlung, relativistic bremsstrahlung. So different physical processes in the very same source produced by the interaction, by the same group of particles that is interacting with different targets in the source. So these sources can be very complex, so they can offer different targets to the incident particles. This is an even far more complex example. This was calculated by two of my students, Carolina Pepe and Gabriela Vida, a long time ago. So here you have synchrotron radiation by incident electrons, synchrotron self-Compton scattering, upscattering of photons coming from an accretion disk, photons coming from a donor star that is in a binary system. Here you have Bremsstrahlung, proton-proton interactions, proton-photon interactions, whatever. So everything together, many, many components, and all this creates an extremely complex spectral energy distribution that fits amazingly well the observational data from radio up to very high energy gamma rays. So this is essentially the job of the high energy astrophysicist when he wants or she wants to study a source. Is the attempt to solve an inverse problem. We get radiation and we try to figure out what the hell is going on in the source. Okay, of course, is a degenerate problem. So there are many possible solutions, and for this reason, there are always discussions among high-energy astrophysicists about which one is the best model for a particular source. So how do we solve these discussions? Well, looking at other energy bands, trying to gather more information and to narrow the degeneracy in the models. Okay, let's continue. Well, we need the particles out of the thermal equilibrium, the relativistic particles that will interact. So somehow, somewhere, these particles should be accelerated. They should be taken from the thermal equilibrium and accelerated up to very high energies. If we are observing, let's say, TeV gamma rays, then for sure, because of energy conservation, our particles need to have higher energies. So it's not easy to accelerate particles up to such energies. We can do here at the Earth, at these energies, using the Large Hadron Collider, but nature can accelerate particles to energies much higher than those. So what are the main mechanisms? Here I am going to repeat a few things that you have already learned with Rafael, but I think it's worth it because these are important things if you are going to be or you are astrophysicist. Well, we have essentially two types of acceleration mechanisms in astrophysics. One, direct acceleration. This is what is called one-shot acceleration. Huge electric field, you put the charge there, it's accelerated. So this requires huge potential drops. And in space, it's very difficult to have that. Why? Because plasmas are formed by equal numbers of charges of opposite signs. So if the plasma is subject to an electric field, the charges will move and very soon will screen the electric field. So there are no large-scale electric fields in the universe. Only magnetic fields are of large scale in the universe. But if we look at compact objects, very compact objects, then in those objects we can have huge potential drops. So this is one of the possible mechanisms. I will go into details in a moment. And then we have diffusive mechanisms. What are diffusive mechanisms? Well, are mechanisms that operate step by step through many steps with the result of producing a power law of particles where most of the particles have low energy and just a few particles reach the very, very high energies. And among diffusive mechanisms, we have three different possibilities. One, turbulent acceleration. This is called Fermi type 2 acceleration. We have shock-mediated diffusive acceleration. This is called Fermi type 1 acceleration. We will see why in a moment. And then you have magnetic reconnection in a turbulent, highly magnetized plasma. So let's have a look at all the things. Let's begin with the one-shot acceleration, direct acceleration. So let me introduce the pulsars. What are pulsars? Are extremely compact stars, are neutron stars. A neutron star is what is left after the explosion of a type 2 supernova. Is a star that is extremely compact in the sense that the radius of this star is just 10 kilometers, but the mass of the star is 1.4 solar masses. So if you make a very simple calculation, like this one here, you will see that the density of these stars is huge. The average density is around 6 times 10 to the 14 grams per cubic centimeter. That is a lot. Of course, there is a structure in these stars. We have a crust on the surface of the star. And then below the crust, we have some superfluid formed essentially by neutrons, hence the name, a neutron star. And then in the interior, nobody knows for sure what is going on, but very likely there is a plasma formed by quarks and gluons. So essentially the density of a neutron star is the nuclear density. So we have a star with the density of a proton or a neutron. And that is an amazing physical object. And in this superfluid that the star has inside, there are currents. And these currents are not dissipative, so they can keep strong magnetic fields. So if you have a current in a sphere, magnetized sphere, you will have a magnetic field of this shape, something like, at first approximation, a dipole. So you see, this is the magnetic momentum of the star, and here you have the close field lines of the dipole. And the whole thing is rotating. It could rotate very fast. This magnetic field close to the surface could be extremely high, of the order of 10 to the 12 Gauss. If the star is very, very young, it can be a magnetar. A magnetar has even stronger magnetic fields that can reach 10 to the 15 Gauss. These are the most intense magnetic fields in the universe, those in magnetars. Okay. Now, let's think in the neutron star as just a conducting sphere. So it's rotating very fast, and we have this magnetic field that is produced by the currents inside. And then charges on the surface that is conducting will undergo the Lorentz force. This omega is just the angular velocity of the star in its rotation. It's related with the period through this simple expression. B is the magnetic field, and well, this is the electric charge, and this is the radius of the star at the surface. So you see that there is a force that acts upon the charges on the surface of the star, and here you have the charge, but we have charges of opposite sign. So these charges are separated. When you separate charges, you send some positive charge, let's say, to the north magnetic pole, and the other, the opposite charges to the south magnetic pole, you create a huge potential drop. So what is the potential drop? Well, there will be this electric field that will be produced by the rotating magnetic field, exactly as a dynamo. When you go in your bicycle and then you have a dynamo and you produce a current. The current appears because you create a potential drop. Then here is exactly the same, but the potential drop now is huge. It's 6 times 10 to the 16 volts. Now, there is an additional problem that does not appear in the ideal case, and the problem is this. Since the star rotates very, very fast, at some distance from the star, the closed lines will start to move faster than the speed of light, and that is not possible. So, yes? Can you speak? It's not homogeneous. It's a dipole magnetic field. So as you go away from the star, it goes as the distance to the -3. Sorry? Yes, and the poles is more homogeneous, but I will go to that point just in a second. So at some distance, the magnetic field lines cannot co-rotate rigidly with the star, because otherwise they should move faster than the speed of light. So what happens? The field lines becomes open, like this one or this one here. To say that they become open, that means that they close at infinite distance. But now this creates a new situation. Why? Because of the electric field, and through these closed lines, charges can move from the north pole to the south pole, and then can screen the potential drop that we calculated a moment before. So this screening occurs all along the surface of the star, except in the region where the open field lines appear. This is a very small region close to the magnetic pole of the system. More or less, the radius of this region is 100 meters. And all the radiation that we receive from the system comes from the open field lines. So particles now escape from this line. They will produce a wind, particles that are ejected, and when they are ejected, they produce radiation in the radio regime, but also they can be observed even in gamma rays, and they pulsate, and hence the name of the system, pulsar. Why they pulsate? Because the thing is rotating, and if the rotation axis is not aligned with the magnetic momentum, it's like a lighthouse. So when it points to you, you see a rise in the intensity, and then you wait a period, and it appears again. Now, all the power that could be 10 to the 36, 10 to the 37 Hertz per second, that is almost 100,000 times the total luminosity of the sun, comes from this small region of 100 meters in the surface of the star. It's amazing. Okay, but then here the electric field is not screened. It's not screened because the particles just escape. And then there we have the possibility of accelerating charged particles by one shot. And now if we replace in our previous expression for the potential drop, not the entire radius of the star, but the size of the region from where the open field lines emerge, we get this expression that can be rewritten like this, and in convenient units is something like this. So this gives you the typical potential drop in a pulsar. For a pulsar with, let's say, oh, sorry. I am going the wrong direction. Sorry. Again, here. So for a pulsar with a period of the order of 1 second, we will be in this order of magnitude of 10 to the 12, 10 to the 13 volts. So if I put a charge there, the charge will escape with an energy that will be 10 to the 13 electron volts. Sorry, and these particles are accelerated and escape from the light cylinder and go away, like a frozen wind along the magnetic field lines until some distance where the bulk motion of this outflow will be converted in internal energy of the particles and we'll get a hot plasma. Okay. So, well, this was what I was saying about the pulsar. So you see the radiation escapes in the direction of the magnetic momentum, and this is what you observe, for instance, in radio. If you point your radio telescope to a pulsar, you get a signal like this, very regular signal. And from changes, this is just a comment, but from changes in this signal, very rapid small changes, you can infer changes in the neutron star. And you can make inferences about the equation of state of the matter in the interior of the star. That is, yes, glitches and this kind of thing. So it's quite, there is a whole world regarding neutron stars. But what now I am interested in is what happens near the polar cap. In the polar cap, some electron, this is the surface of the neutron star. Here we have this potential gap, and then an electron can be just ejected from the surface, and then it is accelerated by the electric field along the magnetic field lines. The zero radius is so small that the particle moves along the magnetic field line. And since the magnetic field line is bent, there will be curvature radiation because the electron will be accelerated. So then the photon will be emitted. This will be a high energy photon, a gamma ray photon. And then the photon will interact with the magnetic field. This is a quantum interaction because it's an interaction between the photon produced by the curvature radiation with a virtual photon that is associated with the magnetic field. So this photon-photon annihilation produces an electron-positron pair here in the gap. And since we have this electric field, these charges are separated. One is directed in the outward direction, and the other one is directed towards the surface. When it goes to the surface, it radiates also, but now in the direction of the surface, creating new pairs and giving rise to a self-sustained mechanism that extracts from the magnetic field a lot of pairs. All this wind of particles that emerge from the pulsar comes from this mechanism. Fascinating. Okay. This is the real thing. So, for instance, this is the Crab Nebula. In the middle of the Crab Nebula, you have the Crab Pulsar. The Crab Pulsar is right here. This is an image with the Chandra X-ray telescope, and this is an image with the Hubble Space Telescope. And what you are seeing here is this outflow of particles in form of a collimated wind that you see escapes from here and forms a huge bubble that is called the pulsar wind nebula around the pulsar. These are the famous pulsar wind nebula. Sorry. And a similar effect can be obtained also in black holes. You will say, how, if there is no surface in the black hole? Well, there is a trick here. If you have a rotating black hole, perhaps you know that the system has what is called outside the horizon an ergosphere. So the Kerr solution for black holes present an ergo region around the black hole. In this ergo region, things should co-rotate with the black hole because space-time itself is rotating. So it's absolutely impossible to remain at rest as seen from infinite if you are in the ergosphere. So now imagine the following situation. You have an accretion disk around the black hole, and in this accretion disk there are currents, and this currents has large scale poloidal fields. So this poloidal field is accreted to the black hole, and at some point it will penetrate in the ergosphere. When it enters the ergosphere, it cannot remain purely poloidal. It will be developed a toroidal component, as you can see in these simulations here. So the magnetic field starts to twist inside the ergosphere and forms this kind of magnetic tower, and this produces a pointing flux in the direction of the rotation of the black hole. And there is another interesting effect, because if you have a rotating magnetic field, what do you create according to Maxwell equations? An electric field, of course. And then you will have some potential drop just above the pole of the black hole. Now, this gap is very sensitive to the creation of electron-positron pairs. Why? Because if there is a lot of matter there, then charges will separate and will screen this potential drop, and the potential drop will disappear. So what we think happens is that this electrostatic gap appears only in black holes with very little accretion. If you have system with a lot of accretion, close to the Eddington limit, for instance, there will be no gap because it will be screened by charges. But in starred black holes is possible, and it has been suggested that, for instance, starred black holes could accelerate just by one shot ultra-high energy cosmic rays up to energies of the 10 to the 20 electron volts. So this is another example of a one-shot acceleration. This is the maximum potential drop that you can achieve for a maximally rotating black hole. And you see that if you have a supermassive black hole here, then very easily you can get 10 to the 20 electron volts. It's quite interesting possibility. Okay, enough for one-shot acceleration. Let me now move to diffusive acceleration. You already have seen this, so I will move faster. I just will emphasize the physical concepts. First, turbulent acceleration. What is the basic idea here? Imagine you have a wall and you have a ball. And this is an elastic ball, so you throw the ball to the wall, and then there is an elastic collision. And imagine that the velocity of the ball is v, and the velocity of the wall in the opposite direction is u. Let's call it u. I use also capital V, but it's confusing. So from the point of view of the wall, you will see the ball coming to you with a speed u plus v before the impact. And after the impact, you will see the ball just moving away from you with the inverted velocity, u plus v. Now, if you transform to the lab system, the energy will be 2 times u plus v. So there will be a gain of energy in the ball. Now imagine that you have 2 walls, and these walls are moving in converging directions. So each impact, the ball will gain energy more and more until the walls stop or until the walls become transparent to your ball, and the ball will escape. Well, this is essentially the situation, but now imagine just a random distribution of scattering centers, for instance, magnetic inhomogeneities, and replace your ball by a charged particle. So you inject your charged particle in this gas. This is an example of a turbulent gas with many different dispersion centers that moves in any direction, just isotropic direction. So some collisions will be head-on, and the particle will gain energy, and some collisions will be tail-on, so the particle will lose energy. So what is the secret for the energy gain? That the head-on collisions are more likely than the tail-on collisions. So the average energy gain in a cycle inside one of the systems goes like the velocity of the dispersion centers divided by the speed of light to the square. So if this velocity is low, this will be a very small number, and then the energy gain will be small. For this reason, this mechanism is not very efficient. You need a lot of time in order to get a lot of energy. So you can calculate very easily from this expression what is the energy gain for the particle after a time delta t, and you will see that is proportional to the energy. And we can write this expression just like this, alpha, where alpha is all this constant. This is the velocity of the dispersion centers, and L is the size of your plasma region. And we have this expression. So what is the energy distribution that we get from this process? Well, if we want to know that, we need to solve the transport equation in steady state. What is the transport equation? I guess that you already have seen this. It's an equation that is a version of the Fokker-Planck equation. This gives us the number of particles with energy E, how this number of particles changes with time. So if this is different from 0, then something should happen to your population. So particles can diffuse. This is the diffusion term. This is the diffusion coefficient. Or particles can gain energy or can lose energy through different mechanisms. All that is taken into account in this term. Or particles can be removed from this accelerator, for instance, by a wind or for some macroscopic motion. And we could have also injection of fresh particles that we need to take into account. So essentially, this is a conservation equation. And now in the steady state, this is 0. We can neglect the diffusion of the particles, and also we can neglect the injection in a closed system. So the equation now reduced to very simple differential equation, that is this one. And now we remember that the energy gain of our particles is proportional to the energy. So here I replace the gain by this alpha epsilon. Epsilon is the energy. And then we only have to solve this equation, where this is the escape time for the particles, and we get this solution, a power law. Power law where the power law index, x, is related to the constant alpha, that in turn is related, remember, with the size of the region and the velocity of the scattering centers, and the escape time scale for the particles. So this index is model dependent. So there is no a universal index for this process. You need to study your source. You need to know the size of your source. You need to know what is the average dispersion velocity in your source. But in principle, it produces a power law. That is what we observe. You will say, well, perhaps this mechanism is so slow that never happens in the real world. But no, it could be important, for instance, in giant radio lobes of galaxies where you have a lot of gas and turbulence, or in the Fermi bubbles above our galaxy, or in many different situations. So slow doesn't mean not effective. The other mechanism is Fermi 1. And here the difference is that we can now make energy, put energy in our particles much faster. And what is the secret? The secret is the introduction of a shock wave in the process. So what is a shock wave? A shock wave is a discontinuity in a fluid, for instance, the interstellar medium. So in a discontinuity, you have a situation like this. You have the shock that moves supersonically in the medium. And then we have two regions. The post-shock region that is already shocked, that is this region here. This is in the system of the shock. The shock is not moving in this system. We are moving with the shock. So this is the post-shock region, and this is the pre-shock region, and the different values of the velocity of the fluid, the density of the fluid, and the temperature of the fluids are related by the Rankine-Hugoniot relationships. And what are these relationships? Just conservation laws. Conservation of mass, conservation of momentum, and conservation of energy. Conservation of mass, because I am assuming, for simplicity, that particles are not being created in this process. If we have a magnetized medium, then it's very easy to transform these simple equations in these other equations where I am just taking into account the magnetic energy, density, and the role of the magnetic field. So if we have a monoatomic gas, for instance, hydrogen, and the shock is very strong, yes? H is the enthalpy. Yes, sorry, it's the enthalpy, and U is the velocity of the flow. Then the ratio of the density and the ratio of the velocities is 4. That is the number. So let me show you now how this works and why this works so well. You will see that this animation is in the system of the shock. So the shock is immobile, and then we here have the pre-shock region. So the gas comes to us at high speed, the same speed of the shock, and this here is the region shocked. And in the region that is shocked, things are more dense, so the scattering centers move slowly, more slow than in the pre-shock region. And this will make all the difference, because the particles will not lose so much energy in tail-on collisions in this region. And they will win a lot of energy in head-on collisions in this other region. Let's see. This small red dot here represents the particle. So let's see how it gets energy. Sorry, this is the post-shock region. This is, and this is the pre-shock. The shock is moving in this direction. So you see, this is a head-on collision. The particle gains a lot of energy, and then disappears, escapes. The system cannot contain anymore the particle. So the more energetic the particle is, the more difficult is the particle to be contained in the acceleration region. Well, and you will say, okay, I can imagine that I have magnetic scattering centers in the post-shock region, because once the shock passes, produces a lot of turbulence, and then I have inhomogeneities in the magnetic field. But what about the pre-shock region? Well, why? If this region is not perturbed, why there are scattering centers there? And the answer that was found in 1978 by Weibel and Tony Bell is that the particles themselves that goes from downstream to upstream perturb the magnetic field in the pre-shock region, creating inhomogeneities because of the now so-called Weibel instability. It's a current that perturbs the magnetic field. So this produces the backscattering of the particles to the downstream, and then the process repeats. So it's very easy. I left this to you as an exercise to show that for a strong shock, the power law that you get goes as the energy to the -2. And the acceleration time scale, the time it takes for the particle to reach an energy E, is given by this expression. It's the derivative of energy respect to time over the energy. So this is the energy gain per cycle divided by the time that takes for a particle to do a cycle. And this expression here in the numerator is just linear in the velocity of the shock divided c. Remember that in the previous case, there was a square. Now it's linear, so now this is far more efficient. And the time it takes for the particle to make a cycle will depend on the shock velocity and the diffusion coefficient. And the diffusion coefficient is normally a function of energy, and in a strongly magnetized regime, it can be approximated by bond diffusion. So it's easy to calculate. Of course, this is just the ideal case. There are a lot of effects that can make things far more complicated. For instance, while you are accelerating cosmic rays, these cosmic rays accumulate in the acceleration region and they produce pressure. And this is a relativistic fluid with an equation of states that is 1/3 of the energy density of these particles and will produce a deformation of the shock. This deformation of the shock will, in turn, will have effect on the acceleration process in a nonlinear relationship. So if you want to calculate things in all detail, you need to make simulations because all these nonlinearities that appear makes just simple analytical calculations almost impossible. And just for your information, a few weeks ago, by first time, it was observed, and it was published in Physical Review Letters, Fermi acceleration in the lab, using cold atoms. Very modest energies, but this shows by first time that the mechanism is efficient and can be reproduced in the lab. This is an amazing result. Okay, now in space, how can we produce a strong shock? Well, in the way we produce strong shocks in normal, not normal, in the life of the human beings, just blowing up things. So here you have a bomb, and now this bomb, blown. A lot of energy is released in a small region of space, produces a shock wave that finally reaches the camera and probably cause some problem to the camera. Okay, and in space, well, in space we have supernova. Supernova are the explosion of massive stars. They implode to form a neutron star, and the infalling matter bounces on the surface of the neutron star and is expelled as a huge explosion that can deposit in the interstellar medium 10 to the 51 ERG, a lot of energy. In some cases, the star can implode directly to a black hole, but when the supernova occurs in more or less spherical way, then a neutron star should be produced. And then, sorry, we have a forward shock that moves into the interstellar medium, and we have a reverse shock that moves into the material that was expelled by the explosion. In the same way that when you hit a wall with your fist, there will be a wave that propagates through the wall, but also there will be a wave that propagates in your arm, and probably will break your arm. Okay, the final mechanism for acceleration, diffusive acceleration, is magnetic reconnection. Here we have a situation in ideal magneto-hydrodynamics where the fluid just carry along the magnetic field lines. So imagine that I have two converging currents that drag the magnetic field with them. And then at some point, the magnetic energy density here will be much higher than the energy density of the fluid. So the fluid becomes magnetically dominated. Ideal magneto-hydrodynamic is not valid anymore. And then we can have a sudden change in the topology of the magnetic field. So there is a reconfiguration of the magnetic field lines. And now the field moves in this direction, and when it moves, it takes the matter with it. And that is impulsive, so that will never produce a power law. But you could have many sheets with different polarity in the magnetic field in such a way that these magnetic islands are formed. This is a simulation by Kowal, Dalpino, and Lazarian. And you see that these islands are formed. And inside these islands, particles are trapped. The island closes because of the magnetic tension. So the particle bounces in the walls that are moving inwards, and the energy of the particle increases and increases. When the particle is energetic enough, escape from an island and is captured by another island, and the process repeated. And this is a diffusive process. So the final outcome will be a power law. And the power law now will depend on the magnetization of the system. The higher the magnetization, the harder the power law. So this mechanism allows to produce a wide variety of different slopes in your power law. It's a versatility that is not available to shocks. Okay. Well, of course, this type of events occur frequently in the sun, in the Earth magnetosphere, and in the solar system. So this physics is very well understood because we can send spacecraft and study in situ these processes. Well, I will say in what remains some words about the targets. I was talking about the particles, the projectiles that I want to use to bombard my targets. But what about the targets and the interactions? So let's review the most important targets. The most important is matter. So I can accelerate by some of the mechanisms that I mentioned before, protons, and then I can throw these protons through some target form, for instance, by hydrogen or a molecular cloud or some material. So the interaction will be proton plus proton. When two protons or a proton and a nucleus interact, approximately 50% of the kinetic energy of the proton is transferred to one of the quarks in the other proton. So this tends to separate the quark from the proton, and since the nuclear force opposes to that, then the energy density inside the proton increases. The proton becomes an excited particle, a delta, that is nothing else than a proton with a quark in an excited level. And after 10 to the minus 28 seconds, this quark just this excite and produce a pion, a proton and plus a pion. The pion, the neutral pion takes approximately 70% of the kinetic energy of the incident proton. So since this neutral pion will decay into gamma rays, each gamma ray will take approximately 10% of the kinetic energy of the incident proton. Then we have another 33% of the energy that goes to produce what is called a fireball. So what is a fireball? What is the number of pions, charge and neutral pions that are produced with a high multiplicity that depends on the kinetic energy of the incident proton. So the multiplicity is given by, for the pions, is given by this expression. Experimentally, this exponent is around 1/4, and this number is 3.3. So approximately 11% of the energy goes to this part of the fireball, and 22% of the energy goes to this other part of the fireball. Since these charged pions decay given neutrinos, the neutrinos will take about 10% on average of the kinetic energy of the original proton. So the result is that after this interaction, you will have high energy photons from the neutron pions, and you will have neutrinos and electron-positron pairs from the decay of the charged pions. Okay. So if you want to calculate now the emissivity, the gamma ray emissivity, first of all, you need to know what is the pion emissivity, because it's a two-step calculation now, because the gamma rays are mediated by the pions. So the pion emissivity is given by this expression. This is the cross-section for pion production in interaction with protons. Proton losses are given by this expression. This is the density of the medium. This is the speed of light. This is the inelasticity, that is of the order, as I mentioned, 50%. And this is the cross-section. This cross-section, contrary to electromagnetic processes, cannot be calculated just from the scratch using quantum electrodynamics, but we can have nice fits from the Large Hadron Collider. All this is physics in well-known energy regime. And this is a very good fit of the cross-section. So more or less below 1 TeV, the value of the cross-section is of the order of 35 millibarns. And then with energy, the cross-section increases as you see here. If you want to use a very good parametrization that is very useful in the calculations, you can use this one that is here, that comes from this fundamental paper by Kellner, Aharonian, and Bugayov in Physical Review D. So if you work on this field, that paper and the other paper from 2008 for proton-photon interactions are your Bible for calculations. Now, we have some other type of interactions with matter, electromagnetic processes. Here we have exact cross-sections, so you can go to the classical review by Blumenthal and Gold. If I remember correctly, this is a review of modern physics from the 70s. And, well, this is a relativistic Bremsstrahlung, and it depends on the cross-section from Bremsstrahlung. That is an exact cross-section, so you can calculate this without problem, and you can use our expression for the emissivity, and then you can get the luminosity. Regarding to pair annihilation, that is another electromagnetic process, you can calculate the luminosity if you have an expression for the annihilation rate. you need to know, of course, what is your density of electrons, your density of positrons, and the annihilation rate is given by this expression that can be obtained also from first principles. So with this, you can calculate the annihilation line in a system where you have electrons and positrons. Sometimes this line could be very broad because the distribution in energy, the distribution in energy of the electrons and positrons could be also broad. So there is a broad line. And actually, this broad line is observed mainly from the galactic center. It was discovered in 1972 by balloon detectors. The first detection occurred in that year with a balloon that was launched from South America, from Paraná in Argentina. And then the line was detected by several other experiments, most recently by SPI detector in integral satellite. So as you see, the line that comes from the center of the galaxy is quite broad, and probably is a superposition of contribution of different sources. One could be the supermassive black hole at the center of our galaxy, but also we have a microquasar there that is called the Great Annihilator that seems to be a powerful producer of positrons. Okay. Another type of targets is photon fields. This gives rise to another electromagnetic process, well known, inverse Compton scattering, inverse Compton upscattering, let's say, of lower energy photons. Here we have an energetic electron, and it interacts with a photon of lower energy, so the electron gives energy to the photon and produces a gamma ray. And as long as there is no pair production in this interaction, we are in a classical regime. So the cross-section is the Thomson cross-section because this is an electromagnetic interaction. But when we start to produce electron-positron pairs, then most of the energy is channeled through this pair production. So the cross-section for just upscattering of the photon drops dramatically in the so-called Klein-Nishina regime that should be calculated using quantum electrodynamics. Well, I do not have time to go into the details, but the important thing here is that the losses for the electrons in the classical regime goes with the square of the Lorentz factor of the electron and the energy density of the photon field. Notice that this expression is almost equal to the energy losses for particles, electrons, moving through a magnetic field, synchrotron radiation. The only difference is that instead of having the energy density of the radiation field, in the case of synchrotron radiation, here you have the energy density of the magnetic field, B squared divided 8p. In CGS units. So, since all other factors are exactly the same, if you want to know in advance, in a certain region of space, which process is more efficient, inverse Compton or synchrotron radiation for electrons, then you just have to compare to make the ratio of these two expressions. The radiation energy density with the magnetic energy density. According to the result, one process or the other will dominate. So you do not need to calculate all processes. You can make in advance just a preliminary exploration of how are the losses, and then you choose what you need to calculate. Okay. One other important thing is when you are in the Klein-Nishina regime, now interactions are very scarce because the cross-section is quite small, but when an interaction occurs, the entire energy of the electron just goes to the photon. So this produces hard spectra in the high energy band. In the case of the classical regime, well, you have this relation between the energy of the photon and the energy of the electron. This is the Lorentz factor of the relativistic electron. Okay, and then if you want to calculate the emissivity of your source, you need to know what is your injection of relativistic particles. Normally, this will be a power law of electrons. And then you need to know your photon field. And here you have many options. For instance, a thermal photon field, for the photon field from a star, for instance. This is more or less a black body spectrum. Or you could have the photon field of an accretion disk. This is a multicolor black body spectrum, very broad. Or it could be synchrotron radiation. Then you will have a power law there. So the result of this calculation will depend crucially on what is your photon fields. Many times, this photon field is attached to all the radiation processes in the same computation. So things could be very, very complicated. And this is the expression for the general losses. Well, and then we have a photo meson production and also Bethe-Heitler effect. This morning, Rafael was talking a bit about this. What is important to know here? When a proton interacts with a photon, the photon excites the proton. So some of the quarks goes to an excited level, and the proton becomes delta. So this delta decays almost immediately, 10 to the minus 28 seconds, and can give us a charge pion plus a neutron in 1/3 of the cases, or in 2/3 of the cases, a neutral pion plus a proton. This neutron is quite interesting. Why? Because it's produced with a very high Lorentz factor. You remember, a proton lives in the lab frame 886 seconds. But if it has a Lorentz factor of, let's say, 1 million, will live 1 million times longer. So that proton can travel a large distance before decaying and injecting a proton and an electron. And this is important because neutrons do not feel magnetic fields and can escape from regions that are strongly magnetized. So there is a lot of interesting physics that is not completely explored in this process. And of course, in order to make calculations, as before, the equations are the same. You need adequate parametrizations for proton-photon interactions. And these are just some very simple parametrizations. If you want some more complex, please go to Kellner and Aharonian paper in Physical Review D from 2008. Okay. Of course, if the proton has energy enough, can produce also a fireball, and things can be quite messy. Okay. And regarding the energy losses for the proton moving through a photon field, okay, they will depend on the nature of the photon field. For instance, this is for a thermal photon field characterized by a temperature T, and this is for a non-thermal photon field with a spectral index of -2 in the photons, in the seed photons for the interaction. Okay. And then we have Bethe-Heitler process. You have a couple of posters, very nice posters here about Bethe-Heitler process. It's a process that is completely underestimated by high-energy astrophysicists. We, with Lucas Paskevich and Leandro Baroa, we are working on some very interesting effects related with Bethe-Heitler pair production. Why? Because a high-energy proton can produce pairs and inject these pairs directly with high energies in media that perhaps are completely magnetized and it would be impossible to accelerate from the scratch this electron-proton pair because of the synchrotron losses. So you could have synchrotron radiation without acceleration of your electrons, just creating your electrons with high energies through this process. So this is a quite important process. And you can combine all together and create cascades. Cascade, for instance, that can be initiated by a proton that is injected in some media with a lot of photons. Then you produce neutrons and charged pion. The charged pion produce electrons. The electrons produce synchrotron radiation. The neutrons inject then new protons. These protons can produce other pions, and you have synchrotron, inverse quantum. You have everything. So it's something quite complicated to calculate, but it can be done. And just to finish, almost in time, some useful remarks regarding how the spectra of your particles is affected by the different type of losses. Let's suppose that you have a spectrum that is N and with a dependency of the energy. That essentially is a power law with an index alpha. So if your losses are Bremsstrahlung, proton-proton, or adiabatic losses, then the spectrum is not changing. But if you have synchrotron or inverse Compton losses, these losses are proportional to the energy to square, then the spectrum will become steeper. In the previous case, the spectrum was unchanged because the energy losses were proportional to energy. So if you go here with the integral, this remains the same. And in the case of ionization losses, then the losses are constant. So you get a harder spectrum, just if ionization is your only losses. And finally, in the Klein-Nishina regime for the inverse Compton scattering, where the energy losses goes with the energy to the -1, then you get a much harder spectrum. I mentioned this before, you remember? So you can get a really hard spectrum. When you observe a source and you see a very strange, very hard spectrum, probably that is inverse Compton in the Klein-Nishina regime. Okay, I think this is more enough for today. I am open to your questions.
Who has questions?
Thank you for the talk. When you showed the distribution functions for the particles, you said that we can ignore diffusion effects and that we can also ignore the injection function. What do we lose from this? And in which situations this cannot be neglected?
Yeah, they can be neglected in the most simple situations. Normally, things are a nightmare because you have a system of coupled equations where, for instance, you produce pairs in an equation, and then those pairs are an injection for instance, the equation for synchrotron radiation, and then you produce photons in that equation. That is a source for, so you have many equations that are all coupled, and things are very difficult. So these require numerical treatment because these are nonlinear coupled equations, differential equations. So in general, things are quite complicated. But in some situations, you can separate. You have clean sources where magnetic field completely dominates something. Okay, then that is a possibility to make a lot of simplifications. But in complex scenarios like jets, for instance, in active galactic nuclei, or in the corona around the black hole, where you have strong magnetic fields, strong photon fields, you have everything. Well, things are quite complicated.
More questions?
Okay, thank you for the talk. So when you mentioned pulsars, you said that, okay, they are pulsating because their rotation axis doesn't, it's not the same as the dipole orientation. So what does that depend on, the rotation axis and the orientation of the dipole? And is there a case when they coincide?
If the rotation and the magnetic momentum are coincident, then there is no pulsar. Not in the sense that the system is not rotating, but in the sense that the system is not like a lighthouse. So you will not see pulsations. Actually, we think that there are some systems that are in this category. And regarding what makes one orientation or the other are the conditions in the implosion of the star, and those conditions are extremely complex. Nobody knows the details. So in practice, we have just random orientations, and of course, if you have the whole range of possibilities, there is a low chance to have aligned both axes, but it could happen.
So that choice of coincidence is to say isotropic, like all of the possibilities are the same probability.
As far as I understand, yes.
Thank you.
Welcome.
Anyone else?
Yep. Yeah.
Thank you so much for this amazing lecture. I was wondering again about the transfer equation within Fokker-Planck when you try to find out the distribution of protons that you get. I see that usually often people use n over tau escape, as you also shown in the slides. I was wondering, do you think this is a good approximation when you have too many parameters to solve the Fokker-Planck, to just use n over tau, or not exactly?
Well, in astrophysics, the version that is normally used is the one I show. It was first presented by Ginsburg and Sirovatsky in their famous book, The Origin of Cosmic Rays, in 1964. And I think for most of astrophysical situations, that is enough. But if you want to make transport in very dense media, you need to go the full Fokker-Planck equation, because you have another effects. But in diluted media, interstellar media, or jets, or corona around black holes, this is more than enough.
Okay.
And it already is complex.
Thank you.
Any other question? So then we can close it. Thank you very much, Gustavo. And remember that we restart at 4 downstairs at the computer room.